Right now we're going to take a look at this question, which gives us a function f of xy and asks us to first of all find the local critical points and classify them, and then find the absolute max/min on a region. So we'll start with the local critical points, and to do that we need to take our first derivatives, partial derivatives, and set them equal to 0. So here we go. So if you calculate fx, get 3x squared minus 12x plus 12, and we're going to set that equal to 0. And then we're going to get fy, and that is 3y squared plus 18y plus 27, and we're going to set that equal to 0 as well. So with the first one, we can solve that by factoring. Factor out of 3, and the rest of it factors as x minus 2 squared. So clearly that gives us x equals 2. And then solving the second equation, once again you could factor out of 3, and then the rest will factor as y plus 3 squared. Since that all is equal to 0, you solve that and get y equals negative 3. So this gives us our critical point of 2, negative 3. Alright, next we're going to try to classify that. And to do that, we need to find the Hessian. In order to find the Hessian, we will need to find all the second derivatives. So we'll need fxx, fyy, and fxy. So fxx is 6x minus 12. Fyy is 6y plus 18. And fxy is 0. So put that all together and you get that the Hessian equals 6x minus 12 times 6y plus 18, and then just a minus 0 squared. You can leave that off if you want. So now we need to calculate the Hessian at our critical point, which was 2, negative 3. And that's going to be 6 times 2 minus 12 times 6 times negative 3 plus 18. Work that all out and you get 0. So Hessian of 0 gives us no conclusion, and we're just going to leave it there. That's the local part. Now, absolute max/min. We have our local critical point. We also need to find boundary critical points and corner points. And the region that we're given is right there. So, this is a rectangular region, so we're going to break it down into 4 boundaries. The first boundary will be x equals 0. So when x equals 0, f of 0 comma y is going to be 0 cubed plus y cubed minus 6x squared plus 0 squared plus 9y squared plus 12 times 0 plus 27y plus 19. And then we're going to take derivative with respect to y of that, and we get 3y squared plus 18y plus 27, and we set that all equal to 0. Now, of course, this equation is quite familiar. We actually just solved it out. And this will be 3y plus 3 squared equals 0. So you get y equals negative 3. However, looking back at our region, y equals negative 3 is not in R. So it doesn't give us any new boundary critical points. Next boundary piece is when x equals 3. So for that, f of 3 comma y is going to be 3 cubed plus y cubed minus 6 3 squared plus 9y squared plus 12 times 3 plus 27y plus 19. And once again, we're going to do partial with respect to y of this. And since all those x bits only have x in them, those all go to 0, and you'll wind up once again with 3y squared plus 18y plus 27 equals 0. So of course this will solve again to give us y equals -3, and once again we'll note that this is not in our region R. Next boundary, y equals 0. So when y equals 0, that's going to give us the function x cubed plus 0 cubed minus 6x squared plus 9 0 squared plus 12x plus 27 times 0 plus 19. And I'm going to take the partial with respect to x of all that, and I'll get 3x squared minus 12x plus 12, and then the rest will just be plus 0. And this all has to equal 0. Well, once again, when we factor this out and solve, we'll get 3 times x minus 2 squared equals 0, and that gives us x equals 2. This does give us our point on our region. So that gives us the boundary critical point. X is 2 and y was 0. And then the last boundary piece is that y equals 4. And so plugging in 4 for y, we will get x cubed plus 4 cubed minus 6x squared plus 9 4 squared plus 12x plus 27 times 4 plus 19. But once again, when we take the partial derivative, all those constants will go away, and we will wind up with 3x squared minus 12x plus 12 equals 0. Once again, this is just going to solve out to give us x equals 2. By coincidence, these happen to turn out to be the same. And this also gives us a new boundary critical point. X is 2, y is 4. So now we've got our local critical points, our boundary critical points, and we'll fill in our corners as well. And we're going to compare it to see which ones give us the local min, local max. Now, one thing to note is that our local critical point was 2, -3, but 2, -3 is not on our region, so we can eliminate it from finding the absolute min-max. So we will include our boundary critical points, which were 2, 0 and 2, 4, and we'll include our corner points. And for the corner points, since x goes from 0 to 3 and y goes from 0 to 4, we will get corner points 0, 0, 0, 4, 3, 0, and 3, 4. And now we need to plug them into the function to see which one gives us absolute min and absolute max. So plugging in 2, 0, you get 27. Plugging in 2, 4, you'll get 343. Plugging in 0, 0, you'll get 19. Plugging in 0, 4, you'll get 335. Plugging in 3, 0, you'll get 28. And plugging in 3, 4, you'll get 344. So we can quickly see that is our absolute min, which we could write as the point 0, 0, 19. And this is our absolute max, which if we give as a point would be 3, 4, 344. Of course, the absolute max value would be 344. It's different ways to write down the answer. And there you go.